quote from Brian Cox could be shocking. It would shine like a second sun because it's only 600 light-years away. The red supergiant Betelgeuse could be about to explode. Images show that Betelgeuse has completely dimmed and become very unstable. Researchers around the world are eagerly awaiting this unique event. At a distance of just 600 light-years, we on Earth will be able to see the spectacle with our naked eyes. When Betelgeuse explodes, it will shine brighter than the entire galaxy for a few moments. Even weeks later, we will still be able to see the remains of the supernova. What exactly will happen when Betelgeuse explodes? According to astrophysicist Brian Cox, we will see a light so dazzlingly bright that for a few moments, it will look like a second sun during the day. We might be blinded for a short time and see a very bright flash. If the star explodes at night, it will be as bright as day for a few moments. Betelgeuse is about to explode, that much is certain, but on a cosmic scale, shortly, could mean 100,000 years or even just one day. The crazy thing is that Betelgeuse could already have exploded, since the light from the supernova will travel through space for 600 years before it reaches us. We will only see the extreme brightness 600 years after the actual explosion. This idea highlights the extreme dimensions of the universe in an impressive way. It will be exciting for us as soon as the supernova becomes visible, and we are already following every little change in the star. In 2019 and 2020, the red supergiant Betelgeuse experienced a dramatic decrease in brightness, which subsequently became known as the Great Dimming Event. This sudden drop in brightness led to speculation that the star was about to explode. Some experts believed the star would brighten shortly before the final event. Researchers eventually found that the dimming was caused by a huge ejection of dust that blocked some of the star's light. It is likely that the aging star Betelgeuse experienced a mass ejection, a phenomenon also observed in our Sun, where large quantities of material are ejected into the surrounding area. Betelgeuse is 1,000 times larger than our Sun, and the amount of material ejected was much higher. The dimming was caused both by the dust cloud and by the star experiencing cooling at the site of the material loss. In March 2024, the American Association of Variable Star Observers reported that Betelgeuse had again experienced a dip in brightness of about 0.5 magnitude. Researchers anxiously and excitedly observed the dimming since late January. This dimming was another sign that we do not fully understand Betelgeuse, and any unusual change could indicate an impending explosion. Again, the scientific community researched intensively and eventually found that the extreme dimming was a direct after-effect of the Great Dimming Event of 2019 and 2020. Now, brand new studies and simulations from astronomers at the Max Planck Institute for Astrophysics suggest that the turbulent surface activity of Betelgeuse could also lead to optical illusions. So what is the real status of the red supergiant, and will we see the explosion soon? The theory of a binary star system suggests that while it has been proven that Betelgeuse is well on its way to going supernova, it remains a mystery as to what stage the red supergiant is in. Betelgeuse is not a normal red supergiant. It behaves differently from other stars of its type observed in space, and there could be an unknown reason for this. Some of the star's characteristics do not fit the typical picture, which led researchers to propose a fascinating theory. Betelgeuse could be the result of two smaller stars merging. If this theory is correct, we would not be observing a single old star on its way to going supernova but rather the product of two. The star rotates quickly and contains more heavy elements such as nitrogen in its atmosphere than is typical for red supergiants. A simulation carried out by astronomers showed that Betelgeuse could originally have been a binary system consisting of two stars. One of these stars would have attracted the mass of the other, ultimately leading to a merger. This process would have disrupted the internal material of the newly formed star and pushed the heavy elements into its upper layers, explaining the unusually high concentration of nitrogen. The merger would also have accelerated the rotation of the star. Normally, red supergiants rotate much more slowly. However, the simulation plausibly showed that the additional transfer of angular momentum could be explained by the merger of two stars. A counter-study showed that the fast rotation of the star could also be a misinterpretation. The activities on the surface of the star can lead to optical illusions that give the appearance of increased rotation. Betelgeuse's actual state is therefore very difficult to assess. The only scientific certainty at present is the activity of violent deep convective currents that are constantly pushing billions of tons of material to the surface of the star, making the core increasingly unstable. Betelgeuse is definitely in a late stage of its development. Scientists suspect that the star is currently undergoing the carbon-burning phase, which typically lasts about 1,000 years. When this phase ends, Betelgeuse could explode within decades rather than millennia, as was originally thought. The renewed dimming of Betelgeuse in 2024 and the fluctuations in brightness could be the first signs that the star is approaching its end. Betelgeuse holds a special significance for us. It is not just any star, it is one of the brightest stars in the constellation Orion, a constellation that has always had special meaning for humans ever since our species began looking up at the sky. This star has been particularly huge, red, and conspicuous. Betelgeuse likely bloated into a red giant more than 100,000 years ago, so we have never known it any differently. But it's only recently that we have become aware of its peculiarity and its fate. The earliest records of Betelgeuse come from ancient Egypt and Mesopotamia, where the star was particularly revered as one of the brightest in the night sky. In the Middle Ages, Betelgeuse was mentioned by astronomers such as Tycho Brahe in his star catalogues. He described the star in the 16th century as conspicuous and reddish, and wondered what this meant. The systematic scientific study of Betelgeuse began in the 16th and 17th centuries when telescopes became much more advanced. Galileo Galilei, one of the pioneers of modern astronomy, observed Betelgeuse and studied its brightness fluctuations in detail. Even then, much more powerful telescopes made more detailed observations possible from the 18th and 19th centuries onward. William Herschel was one of the most important astronomers of the time, and he classified Betelgeuse as a variable star that changes its brightness over time. The decisive breakthrough in our understanding of Betelgeuse came in the 20th century with the development of spectroscopy. In the early 1900s, astronomers were able to analyze the chemical composition and temperature of distant stars for the first time. The spectroscopic study of Betelgeuse showed that the star was a red supergiant in the late stages of its evolution. Edwin Hubble, known for discovering the expansion of the universe, also contributed to the study of Betelgeuse in the 1920s. Hubble used the newly developed techniques of astrophotography to study the size and structure of the star. In the 1950s and 60s, the invention of the radio telescope ushered in a new era. This technology made it possible to observe Betelgeuse in different wavelength ranges, providing completely different insights into its physical properties and atmosphere. Finally, in the 1990s, the Hubble Space Telescope revolutionized Betelgeuse's surface observations, and we witnessed its irregular brightness fluctuations for the first time. Since then, researchers have divided the fluctuations into several almost regular cycles. Since the beginning of the 21st century, we have had the next great technological innovation, interferometry. This allows astronomers to make extremely precise measurements of the surfaces of stars. Observations with the Very Large Telescope in Chile have shown us exciting images of irregular surface activity and huge convection cells for the first time. We have only known the details around Betelgeuse for a relatively short time, making it difficult to make an accurate prediction about its future. The most recent observations in 2024 showed another significant dimming, supporting the theory that Betelgeuse is heading for a supernova explosion. Modern technology such as high-resolution spectroscopy and computerized simulations now allow us to precisely track the state and future evolution of Betelgeuse. While Betelgeuse remains an object of intense scientific study, the chronology of its exploration demonstrates the progress of astronomy and humanity's growing ability to unravel the mysteries of the universe. What do we really know about supernovae? Our science sometimes seems so self-assured, and it's easy to get the impression that researchers possess real truths. But especially when it comes to the universe, many theories and opinions are still based on pure speculation. We know the true nature of supernovae just as little as we can precisely examine them. Certainly, people from many eras have witnessed huge explosions of dying stars, but they have usually been misjudged. The first documented observation of a supernova dates back to 185 AD, when Chinese astronomers observed a guest star in the constellation Centaurus. The bright visitor was visible in the sky for several months and then disappeared. In 2006, the brightest supernova of all time was observed by astronomers worldwide. Records from China, Japan, and the Middle East show that the supernova, now known as SN 2006 GY, was so bright that it cast shadows at night and was clearly visible during the day. This star may have been about as bright as researchers expect Betelgeuse to be. Another famous historical supernova occurred in 1054 when Chinese and Arab astronomers observed a new source of light in the constellation Taurus. This supernova left behind the colorful Crab Nebula, which is often depicted today. In 1572, the Danish astronomer Tycho Brahe saw a supernova in the constellation Cassiopeia. Brahe's detailed records of the supernova SN 1572 were more advanced than earlier accounts because he was one of the first to recognize that the sky is not unchanging as Aristotle had claimed, but is subject to dynamic changes. Johannes Kepler then introduced the concept of the supernova in 1604. Kepler noted a stellar nova in his astronomical diaries and assumed that he had witnessed the birth of a star. Kepler's supernova was the last in the visible range of the Milky Way that could be observed with the naked eye. Basically, we have only known what supernovae really are since the introduction of spectroscopy in the 19th century. Dying stars and their explosions continue to be a subject of intense study and fascination, revealing the ongoing mysteries of the cosmos. It's important to note that the study of supernovae and stars like Betelgeuse has profound implications for our understanding of the universe. Each supernova provides crucial insight into the life cycles of stars, the formation of elements, and the dynamics of cosmic explosions. When a star goes supernova, it disperses heavy elements into space, which are essential for the formation of new stars and planets. This process contributes to the chemical enrichment of the galaxy, impacting the composition of future stellar and planetary systems. Moreover, observations of supernovae help astronomers calibrate cosmic distance scales, improving our understanding of the expansion rate of the universe. For instance, Type Ia supernovae, which occur in binary star systems where one star is a white dwarf, serve as standard candles due to their predictable luminosity. By comparing the observed brightness of the supernova to its known intrinsic brightness, scientists can measure the distance to their host galaxies, which is crucial for determining the rate at which the universe is expanding. Technological advancements in astronomy, such as space-based observatories and sophisticated spectrometers, have allowed for more detailed studies of these cosmic phenomena. Instruments like the James Webb Space Telescope (JWST) are expected to provide unprecedented views of distant supernovae and their remnants, offering new insights into the early universe and the formation of the first stars. Furthermore, the study of supernova remnants, such as the Crab Nebula, provides valuable information about the aftermath of these explosions. These remnants offer a natural laboratory for studying the behavior of matter and energy under extreme conditions, helping to validate theories about stellar evolution and the fundamental forces of nature. In essence, the continuous exploration of stars like Betelgeuse and the resulting supernovae represents a dynamic field of research with the potential to unveil the deeper mysteries of the cosmos. Each discovery and observation not only expands our knowledge but also enhances our appreciation of the complex and ever-evolving universe in which we reside. The study of Betelgeuse and similar cosmic phenomena offers profound insights into the life cycles of massive stars and their eventual demise. These stars, which are crucial in the cosmic ecosystem, play a significant role in the synthesis and distribution of heavy elements throughout the galaxy. Understanding their final stages helps astronomers piece together the larger narrative of galactic evolution. Betelgeuse, as one of the most well-studied red supergiants, provides a unique case for observing stellar dynamics. The star's complex behavior is indicative of the intricate processes occurring in massive stars nearing their end. Its large size and mass mean that it is expected to undergo a dramatic collapse before exploding. This collapse is a critical phase where the core contracts under gravity, raising temperatures to the point where nuclear fusion of heavier elements occurs. The resulting supernova is not only a spectacular event but also a vital mechanism for dispersing these elements into the interstellar medium, contributing to the formation of future stars and planetary systems. Astronomers are also keenly interested in the impact of such explosions on their surrounding environments. Supernovae generate shock waves that can trigger the formation of new stars from the surrounding gas and dust. This process highlights the interconnectedness of stellar life cycles and the dynamic processes driving cosmic evolution.